Hello viewers, welcome back. Say hi to my pet Dino. He's so eager to meet you all. So in this lecture video, I'm going to tell you how to do floating point arithmetic. Floating point numbers are represented with IEEE 754 standard. I have introduced this topic, how to represent floating point numbers, in my previous video. So if you haven't seen that video, please go through it first. It will give you the required foundation, and I'm giving the link for that video here. So just a quick recap here also. The floating point numbers n has a mantissa multiplied by radix to the power exponent. It is basically a real number with a mantissa or significant part. But in scientific notation, it is represented like this: mantissa multiplied by radix to the power exponent. And we are going to see uh, in how many different ways we can write this number. Like the same number, m, if I divide by r, then we have to adjust the exponent by adding 1 there. And if I multiply the mantissa by the radix, we have to adjust the exponent part by decrementing it by 1. So here it is giving the example. Here it is my number, the whole mantissa given here, 1101.0101. So this is a real number expressed in binary form. But in scientific notation, we usually write it like this: 1.1010101 multiplied by 2 to the power 3. You can draw the analogy from the decimal number representation, how the scientific numbers are represented to the power 10. So it is similar to that. It is only radix is 2 here. Now the same number can be represented as 0.1101, and here the exponent is increasing because the mantissa decreased, and similarly for the other representation also. Now, because the same number can be represented in so many different ways, we need a standard way of representation, and that is called normalizing the number. In normalizing the number, we keep 1 in the most significant digit. So it is written here that mantissa has a non-zero value in the MSD position, most significant digit position, then it is normalized. So according to that definition, first number is normalized, others are not. Now we have to see how many digits or bits we can keep this number, right? If the fraction part is very big, it will not accommodate in the data word. So IEEE 754 format has specified number of bits allotted for exponent and mantissa. But before that, this is the organization for keeping them here as a number. So the first bit is for the sign bit of the mantissa, and then comes the exponent, and then come the mantissa. Okay, so first sign, then exponent, and then mantissa. And this sign bit is for the mantissa part, not the exponent part. And mantissa is represented as sign and magnitude binary number. Remember, it is sign and magnitude. So sign here and only the magnitude goes here. And exponent is represented as 2's complement excess k number. We have gone through this 2's complement number, excess or biased representation before also. So at the end of this lecture, the whole playlist of the number system will also be given. Please go through that also. So IEEE standard number is 754, and it was devised in 1985. IEEE stands for Institute of Electronics and Electrical Engineers. and they wanted a standard way of writing the numbers so that it is universally accepted, and all computer vendors do the number representation in the same way so that the program can be portable from one computer to another computer without losing any precision of operation in the result part. And this standard has two versions. One is called single precision, which takes 32 bits for data representation or the number representation. And this 1985 started with this single precision number representation. And later in 2008, they also added this double precision number, which uses 64-bit bits for keeping the number. Now, you already know this is the organization of the number. First the sign bit, then exponent, then fraction. For single precision, total 32 bits are there. Out of that, exponent takes 8 bits and fraction takes 23 bits. Now, if you add 23 plus 8 is 31 plus the sign bit, 32 bit. And for double precision number, exponent takes 11 bits and the fraction part takes 52 bits. Total, if you add them all, it will come to be 64 bits. Now the number that it will represent is given x equal to minus 1 to the power s. S is the sign bit of the mantissa. It is either 0 or 1, sign and magnitude representation. Then multiplied by 1 plus fraction. See here, there was no bit here for representing this one. So this one is implied. It has no place here in this 32 bit. So it is getting an extra 1 bit here. So 1 plus fraction is the actual mantissa times 2 to the power exponent minus bias. That means this exponent is biased. And for single precision, this bias is 127. And for double precision, the bias is 1023. And I already told you before why this biased representation. It is for some comparison purpose for sorting numbers. When you have to compare two numbers, it becomes easy to compare them by this biased representation. Now you can see that the significant or mantissa can range from 1.0 to maximum 2, right? Because 1 then point, if all of them are ones, it will all add them up close to 1. So total significant range is 1 to 2. And exponent is excess representation, actual exponent plus bias is given. So this is the standard way of representing floating point numbers for doing computer arithmetic. Now it is shown pictorially. This is for 32-bit format. It has 32 bits here. And for double precision, it keeps 64 bits. It takes 64 bits. And here exponent is 8 bits, here 11 bits, here bias is 127, here bias is 1023. So with bias 127, the exponent will range from minus 126 to 127. So exponent can be positive and negative both. And mantissa is always positive, whose sign bit is here. The front bit is the sign bit. And this is the arrangement. This is the organization of the floating point numbers. Now, these are, if you want to practice how to represent some decimal numbers to floating point numbers, all these examples are given here with their solution also. And this conversion can be both ways. Decimal to IEEE 754 or IEEE 754 to decimal. If you have to convert the other way, so this is the number given in IEEE 754 single precision number. What number it actually represents, the solution is also given. So many examples are given with their solution. I want all of you to practice this, and I am going to show you in more detail how to solve one of the problems from each group. So Suppose you have to represent the decimal number -3. How will you represent it in floating point number? So because it is a integer number, right? So in binary it will be -112 sign and magnitude. And this number is not written as a normalized form. For floating point number, we have to represent the minus sign as -1 to the power 1, and the number, this 1 we will write it as 1.1. As we are decreasing the mantissa, we will be increasing the exponent by multiplying it by 2 to the power 1. Okay, so the fraction will be from here 1 and all 22 bits of 0, right? Total fraction is 23 bits, so total 1 and then 22 bits of 0, and exponent was 1. With this 1 you have to add the bias 127, it will become 128, and this is the binary representation of 128. So if you are representing -3 as a single precision number, this will be your exponent. And if you are representing this number as a double precision number, the bias added will be 1023. It will be total 1024. So this is the binary equivalent of 1024. There should be total 11 bits here. So the single precision number is this sign bit, and then the exponent part, and then the fraction part. And as double precision, this is the sign bit, and then 11 bits of exponent, and then 52 bits of mantissa. Okay, now let's do the conversion in another way from floating point number to decimal. Suppose we have this number represented as a single precision floating point number. We have to know what decimal number it represents. So we already know the sign bit is 1, and we know the fraction part is this 0, 1, 1 here, and exponent is this. So this exponent is actually 131, right? From binary to decimal conversion, it is 131, but this is a biased exponent. So here we are actually minusing with 127. So it will be 2 to the power 131 minus 127. So the number is -1 to the power 1. Then 1 was hidden, right? 1 point. This is the fraction part 0, 1, 1. And this is the exponent. So you do the math and it is coming out to be -22 in decimal. Okay. I hope you have understood this, and I want you all to solve all other examples that are given with solution and verify them. Okay, now let's see the floating point addition and subtraction techniques. There are several steps for doing that, and we will be taking one example. There are two numbers are there, 1.000 times 2 to the power -1, and second number is a negative number, 1.110 times 2 to the power -2. So first number is 0.5 for quick solution or for better understanding, and the second number is negative 0.4375. Now you know that in floating point representation, the mantissa is represented as sign and magnitude. So no need to do the magnitude part anything, because sign bit will come separately. So the first number um, need will be basically subtracted. Second number will be subtracted from the first number, and the result will be 0.001 into 2 to the power -1. So the steps are, first of all, you have to align the binary points. So where is the, here it was first number had 2 to the power -1, and second number was 2 to the power -2. So this is the smaller number. Second number will be shifted towards right. This now this fraction will be this basically this binary point will come in front. So binary point is going in the left hand side. So the second number will be here, and because you made this significant part smaller, you are adjusting the exponent, decreasing the exponent. Now both the numbers have the same exponent. So first step was to align binary points, and then second step. So you are adding a negative number. That means you are doing a subtraction basically. So 1.000 minus 0.111 will come out to be 0.001. And then the exponent remains as before into 2 to the power minus 1. Now in the third step, you have to normalize the result and check for over or underflow. Okay, so this is the result, right? Subtracting these two number, but this is not in a normalized form. In the normalized form, there in the most significant digit there is a 1. That means you will be shifting the binary point to the left, and then you have to adjust the exponent. So it will be more negative because you are increasing the mantissa, you have to decrement the exponent. So in the normalized form, it will become 1.0002 into 2 to the power minus 4. And this one doesn't have any overflow or underflow. This topic I'll be covering later. It also depends on how many bits of data word you are using. Here it is saying 4 digit. Within 4 digit you have to represent. So there is no problem. There was no underflow or overflow. And now in the fourth step, you actually do round and renormalize if necessary. After rounding also, the number may be denormal. So you have to normalize it again. So this is the result, and it comes out to be 0.0625. Okay. Now I will also tell you what is the floating point adder looks like and how all the steps are done one by one. And this floating point adder is very different from integer adder. In integer adder, entire addition happens in one cycle. But for floating point addition, so many steps are there. It takes several cycles. That's why floating point adders are separate. If the same adder will be kept for floating point addition, it will take a lot of time and it will slow down the clock cycle for all other operation. So floating point adders are different, and I will show you how complicated it is. So here it is showing floating point adder hardware, and here the steps are also given as a flowchart. So this is one floating point number, this is the second floating point number. So first of all, their exponents will be compared, and how much, what is the difference between those exponent. By that amount, the fraction of the smaller number will be shifted. So this it is coming here. These two exponents are subtracted, and their difference is found, and it is coming to a control unit. And control unit will tell which fraction needs to be shifted, left or right. Okay, no, it has to be shifted right because you are adjusting the smaller number as per the bigger number. And after that, those fractions will be added. The significance will be added or subtracted as per whether the number is positive or negative, because it is a sign magnitude representation, and the result may be denormalized, so it will be shifted left or right to make it a normal number. And then when you are shifting it, the exponent also needs to be adjusted, either incremented or decremented. and after that rounding will be done, because you have to accommodate the result within the number of bits that is there. And after the rounding, this is also another topic to look into in detail, and if I may prepare another slide for that, video for that. And after that you will be presenting the number as a floating point number representation as per IEEE 754 standard. So let's see the flowchart, what it says. Start, then compare the exponents of the two numbers, shift the smaller number to the right until its exponent matches that of the larger number. Then second step is add the significand and normalize the sum with shifting, either shifting right or left to normalize it, and then you detect overflow or underflow. If there is overflow or underflow, there should be an exception should be raised that something wrong has gone on in this operation. Otherwise, if everything is right, no overflow, underflow, then this fourth step is rounding. And after rounding also you need to normalize. In some cases if it becomes denormalized, and this will be end of the operation. So now I will be solving few things. Here you see we have to add two numbers, floating point addition. So 7.75 is one number and 0.375 is another number. This is given in decimal. Let's do this math quickly in decimal. So the result will be 8.125. But we are learning floating point, so we'll be representing this number in floating point, and then we'll follow the steps that the adder will do. So 7.75 is equivalent to 1.1111 into 2 to the power 2, and 0.375 is 1.100 2 to the power minus 2. Now floating, and I have given it, written it in a normalized form, right? When you are representing this number, you represent it as per IEEE 754 standard. Now what the floating point adder will do? Floating point adder will adjust the exponent of the smaller number. The second number is smaller, so it is doing the shifting of the mantissa part until the exponent becomes same. After the exponent becomes same, it has added them, and you can see after addition it is denormal now, because there should be just 1 point the fraction, but here there are two digits are there. So if you normalize it, it will look like 1.00, and you are adjusting the exponent. And in IEEE 754 standard, the exponent 3 is 3, you have to bias it with 127. So after biasing, 3 plus 127 is 130. So here you see this 8 bits of number represent 130. This is 128 plus 2. So this is the exponent and this is the fraction. See, I have written only this part. I didn't write this one because this one is implied. There is no place for that. So this is the final number representation after doing the addition. In this case, we didn't consider about underflow or overflow or the result becoming approximate, right? So you can see the first number I have used up for in the fraction part, four digits, and here just by for normalization, now this fraction is 5 bits. So maybe when big numbers with many bits are added or subtracted, there is no place for keeping those extra bits after normalizing the number, least significant bit. And in that case, they are lost. But in this case, we are considering that all the bits are there to be accommodated in the data word. So this example is for subtraction of two numbers. So it is same as the addition steps that I have gone through. Here also, to subtract two floating point numbers, the exponent must be equal. If they are not already equal, then they must be made equal by shifting the significand of the number with the smaller exponent. Now in this example, the numbers are 16.75 minus 15.875, and the result is 0.875 in decimal. But we are going to solve in floating point number representation. So the first number 16.75 in scientific notation and in normalized form is this 1.000011 times multiplied by 2 to the power 4. And second number is 15.875. It is 1.111111 times 2 to the power 3. So this is represented in a normalized form. Now we are going to see how the floating point adder will be adding them. So this is the smaller number. Its exponent is made equal to that of the first number. So for doing that, you see this significant part has changed. And now we can align the binary point and we can do the subtraction. But after subtraction, you can see it is a denormal number. So we have to normalize it. So now it is normalized. Now let's represent it as a floating point number, single precision. So this is the exponent, no, -1. So we can add 127, then it will become 126. So you can see the green color bits are for the exponent and it represents 126, and the result was positive, so the sign bit is 0 here, and the fraction part is only this part 1100. The leading one is omitted because it is hidden or implied. Okay, so hope it is clear and you solve and practice all the problems that is given here, and see you next time with floating point multiplication and rounding, etc.